I've been using for a couple of years. Greg Papadopoulos, who was the Chief Technology Officer of Sun Microsystems, did a talk a few years ago about Redshift and Blueshift companies. And we found it as an easy way to categorize companies into the types of users that they are and the kinds of things that they can do. And so I'm going to set the stage a little bit and talk about internet demand. I'm going to borrow some of the things that Jeff just had up here. And we'll go through what the internet superstars can kind of teach us in terms of things that we can do with everyday data centers. And so we heard some great stuff from Dean about what the leaders are doing. Chris and I were talking about there's probably 12 companies, give or take 3, that can do the things that eBay can do. Not everybody has 60 million customers or 300 million auctions going on at the same time. So we'll talk about what's causing the effects, what is causing our focus on efficiency, this idea of Redshift and Blueshift, which comes from astrophysics and things moving away and moving towards you and faster and slower. And then those lessons that we can get. And I'm going to steal from a lot of different sources here. I'll tell you where they come from. This demand slide is one that I use in a lot of different presentations. It's got some of the same statistics that Jeff had. The number that I have to update it, so you'll notice, I don't know if you'll notice, but Jeff's number was 2.33 billion people in January. It's, I just checked it a few minutes ago. It's 2.36 now. It's growing at about 300 users per minute. And so the reason I have to update this slide so often is that I'm off by a few million every time that I don't update it. The trillion devices, the data growth we'll talk about. The new number is now 688 million smartphones per year, and it's predicted in 2014 that the smartphone providers will break 1 billion smartphones per year, 1 billion new smartphones per year, and about 1/4 of those are net new every year. So these are new people that are accessing the internet using a smartphone. It's essentially a computer that you hold in your hand. 40 million simultaneous Skype users. Skype is the largest telephone company in the world now. A few months ago, they set a record where they had 40 million simultaneous users. That's the entire country of France calling someone on Skype. Okay, and Facebook is up to 845 million users, which is an incredible amount that they are expected to go public with here pretty soon. And look at the different devices that are up here. I mean, we're used to the desktops and the laptops and the smartphones, but cars, OnStar and Sync now have 5 million subscribers each. Airplanes, 4 different US airlines have announced that they have Wi-Fi service available on their airplanes. Millions of customers per day have access to Wi-Fi from airplanes. Satellite radios, everything is becoming internet enabled. That's why we talk about the internet of people is growing huge. The internet of things is really just getting started, when we talk about those trillion devices. Moore's Law has been in effect. This chart is one that Max Planck Institute had years ago. That we're tracking straight on that. Anytime you see that there are log scales on the side, you're growing fast. Same thing with last mile bandwidth. It's getting faster and faster to get access to these things from wherever you are in the world. The talk is the most wired country in the world is now South Korea. And they have something like an average speed of 100 megabits per second to their homes, an average speed of that. In the US, it's much lower. The explosive growth of data is one of the things that Jeff talked about. Here's some other statistics. This is from a report that was put together by IDC and EMC Corporation in 2010. Their estimate is that we're going to grow, Eric Schmidt's talking up there, that we're generating something like 5 exabytes of data every 2 days. Now, in case you aren't familiar, here's the scale. All right, so terabyte, petabyte, exabyte, and that IDC and EMC think we're going to get to 35 zettabytes of information stored by 2020. That's only 8 years from now, right? So what does that take to be able to do? Today, it's fairly easy to get a rack of equipment from EMC that will store a petabyte of data, right? This VNX 5700 will store just about a petabyte of data, draws about 6 kilowatts of power. Not too dense for a rack. To store just the 2012 data, we're going to need 3.9 million of these arrays. Okay, at 22 square feet per footprint, we're going to need 85 million square feet of space just to store the data that's going to be generated in 2012. That's something like 600 football fields worth of white space just for the data storage, and a couple of power plants. And we're doubling this every 2 years through 2020. And in fact, that report coming out 2 years ago, it's starting to look like they're a little bit underestimating the amount of data that we're generating, because people are taking pictures. What was the statistic we just had up there? 3 billion pictures per day going on Facebook? 3 billion? And each of these comes off of a smartphone that's got 5 megapixels of capacity, and each picture is a meg and a half of, that's an incredible amount of storage. So big data is going to drive this. Now, people say then, well, Moore's Law is still in effect. You just showed a chart that said we're doubling processor speed. And we know we're doubling density on disks and things like that. Won't that take care of it? Faster machines and more dense disk and better networks? We'll be fine, won't we? Well, in the storage case, that's not going to be the case. This is a chart of areal density, which is how closely they can pack the disks, the bits together on a disk over the last 40 years or so. And you can see that the demand line being relatively constant, doubling every couple of years. We did pretty good in the 1990s and 2000s. We actually caught up with the slope. You know, we were increasing areal density faster than we were driving the demand. But what's happened in the last couple of years is that we haven't had the technological breakthroughs that we did in the mid-1990s and 2000s and the manufacturing breakthroughs, and we're starting to fall behind at something like 25 to 40% per year compounded annual growth. So that means that we're starting to really outstrip, the demand is starting to really outstrip the density, the things that it can do with storage. So we're not going to solve this problem with Moore's Law from the storage side. If we solve it from the compute side, what's going to happen is we're going to have to put more and more into the racks that we put into the data centers. And so this is a chart that says that, you know, in 2000 it was pretty hard for us to build a rack that consumed more than about 2 kilowatts of power. By 2012, you know, we're up to an IBM Blade Center that consumes 35 kilowatts of power, and these are fairly common. I mean, they're not everywhere in data centers, but most people have a rack that falls somewhere, a rack that falls somewhere in that 20 to 35 kilowatts rack, somewhere in their data center infrastructure. And you heard Dean say that he wants to have a whole data center full of them, right? Anybody have an idea where the average pizza oven that's in your Pizza Hut delivery place falls in this spectrum? Commercial double stack pizza oven that's in most of those stores, about 24 kilowatts. Falls right in here. So we're trying to get a room full of pizza ovens to stay cool, run fast, store twice as much data every year. Doesn't sound like that bad of a problem, does it? Or it sounds like a great opportunity for all of us that are designing these things. And to be honest, we have done a terrible job so far. This is data from Digital. That they look at every year, and I've tracked this thing. You know, they do it in North America. They take the survey in Europe. They take the survey, and they publish it. And every year, I hope that you know, this average number is going to move down. And every year, what happens is they survey 3,000 large company data center owners and operators, and the average almost always falls between 2 and 3 watts of power off the utility to deliver a single watt of power to the computers. And if you look at this, 60% of the data centers are actually drawing more than 2 watts of power to deliver a single watt of power to the IT equipment. So we're bad, but the good news is there's lots of opportunity to improve. Now, Google shows us what's possible. They publish their PUE numbers for a portfolio of about 6 of their data centers, and I'm sure they picked the 6 best that they have, which is okay. I mean, because what they're trying to do is they're trying to show what's possible. These are big data centers. They're not like your enterprise data centers. They do things that you can't do. Well, there's no argument about that, but they do say, hey, we've got a portfolio that we're driving down, so that over the last 3 years, they've driven it down from 1.2 to 1.14. That's good. Their best, they'll be honest about it, and they'll say our best in the quarter was 1.12, and every once in a while, they'll talk about the best single day that we had in one of our data centers. If you listen to Joe Cava or Chris Malone talk at presentations, they'll say, we had a day last quarter where one of our big data centers, the PUE was 1.06, you know, and that was a cold day where they had all the economizers on and high load, you know, everything was perfect. But this is possible. You can drive things down if you're focused on this. So what's the difference then, the big difference between those internet providers and some of the enterprise folks that we've been talking about, or the multi-tenant data centers that we've been talking about? This is where we get into this Redshift Blueshift thing. We tend to divide things looking at Moore's Law. At least this is the way that we did it at Sun when I was there, and I think it's useful. So Moore's Law, if you drew a line and said, all right, Moore's Law is doubling every 2 years, storage capacity, you know, the processor capacity, those things are growing at about that speed. And if you superimposed on that a line that was something like gross domestic product, okay, a measure of how the economy is growing in general, which would be what most of our enterprise customers would do, it would be growing at a couple of % per year, right? We'd grow between 1.5% and 3.5% per year in the US. Some of the developing economies are growing faster, some of them are shrinking. But it would be a much flatter line. And to be honest, sometime around 2000, the compute capacity available to folks exceeded the need that they had from a gross domestic product standpoint, right? We don't need my email system to go twice as fast as it did last year. I don't have twice as many employees in general as I did last year. So my ERP system doesn't have to go twice as fast. All those things, I'm being overserved by Moore's Law starting in about 2000. Around the same time, we were seeing the internet bubble. When we saw companies that were of this internet infrastructure, the high-performance computing stuff, software as a services, global consumer services, where all of a sudden it was possible for me to not only serve people in my local geography, but to serve people around the world for things, to be able to store pictures from cameras, to really change the way that business was working. And these companies are growing faster than Moore's Law. There's all kinds of examples. Amazon's AWS, all the picture sites you can think of, the on-site online social networking things. Some of them with legitimate business needs, some or services. Some of them that you may think are just personal, but it doesn't mean that they're not growing fast and that they're not generating revenue. Gaming is one of the fastest growing online services that there is available. And you think, oh, gaming, but they're still generating revenue, they're making jobs, they're employing people, and people are making money off of it. So these kinds of companies tend to be underserved by Moore's Law, right? And if we look at them, so we call those the faster than Moore's Law companies Redshift, because if you're an astrophysicist, a star that's moving away from you faster, the light shifted red. We don't get into that. But they really treat IT as a weapon, right? It is their factory. They're trying to reduce the cost. You heard Dean talking about the cost per transaction or the transactions per watt that he's getting out of that thing. So they're actually measuring how much they spend on a web search or an auction or a video service or a Facebook update, because that's their product. And the cheaper that they can get that transaction, the more profit they make as a company and the better they are as an enterprise. Down here below in the Blueshift line, IT is a cost. It's something to be reduced. Right? Most of the manufacturing companies have had smaller budgets over the years. When there are cost-cutting estimates or cost-cutting things go on, they frequently look at IT and say, we ought to cut some of that stuff. We want to make it as little bit out of our bottom line as we can, because every dollar that I save off of that is a dollar back to the profit, back to the top line of profitability for this stuff. So the question is then, what can we learn from the internet superstars that we can pull down into those Blueshift companies? Not everything that they do we can do, the enterprise folks, but there are things about knowledge and technology and operations that we can pull down in there. And let me give you a couple of examples. First of all, nobody talked about this stuff before about 2006, 2007, the first energy price crisis where oil went up so high. Then people started to share. The Green Grid, which you guys know that I'm the executive director of, was formed. 11 companies got together, and there's some pretty good competitors in here, right? HP, IBM, and Sun. Intel and AMD, these were fierce competitors that said we can get together and agree to work together on efficiency, even though we compete in so many other ways. Google started to participate in about 2009. They'd been very closed-mouthed about their data centers until 2009, and then they said, never mind, we'll tell you what it's all about. And they had a summit. They've had two different summits now. They had one in the US in 2009. In 2011, they had one in Zurich. They're planning to have them up roughly every 2 years to tell people what the state of Google's data center art is, so that others can learn and imitate. And some of the things that Google does, if you look at them, are, again, these have been talked about at different points during the day. They pick great locations. They can go almost anywhere and be able to supply things. This is a picture of their data center that's in the Dalles, Oregon, right? So it's in a site that's right next to a hydroelectric dam. It's cool most of the year. It's just down the canyon from about 8,000 windmills. They have renewable energy, low carbon, free cooling, and they custom designed their servers. When they had the first data center summit, everybody discovered that they didn't have centralized UPSs. They put a battery on each server. and said that that's about 10 minutes. So they had 99% efficient UPSs. They put in less redundancy because their software can work, like Dean talked about, it can redirect to different data centers. They shift load from one data center to another, and they had modular designs. So if we were to say, out of this list, what could enterprise companies or multi-tenant companies do? I would say it'd be something like this, right? You can't necessarily pick your location. We're going to buy servers. Our customers are going to buy servers from standard providers. But we might be able to pick up some things on free cooling and modular design. And well, let's look at some of those ideas in terms of what we can learn from Google. Now, I should say that there are some things that Google has thought about that even they won't use, right? This is actually a copy of a patent for a floating data center that's powered by wave action, right? And as far as I know, I haven't heard about a Google data center yet. I know I've talked to Joe Cava at every conference I go to, and he hasn't told me about a floating one yet. So they have built one right on the edge of a lake, so they're getting close. But there are some things that even they won't do. So free cooling. These maps were put together by the Green Grid a couple years ago. We said, this is the potential for free cooling. If you run your data center at the ASHRAE recommended ranges, so less than 81 degrees Fahrenheit for the temperature, less than 56 for the, and the dew point less than or equal to 56, so that these are the hours that you could get in the different locations in North America and in Europe for using it. If you look, Dallas is down here. We're still in a 4,000 to 5,000 hours per year range. Wayne showed you calculations that said we could get 4,600 hours per year in Dallas just by opening the windows, so that when the conditions are cool enough and dry enough that we could do things. And I just looked at the weather a little while ago. It's 86 degrees outside with a 68 degree wet bulb temperature right now. So we couldn't do direct air, but we could do water-side economization at this point, right? So here's an hour that we could get out of this. Now, ASHRAE has actually been working in partnership with the Green Grid for the last couple of years, and they've updated their data center standards. They developed them in 2004. They updated them in 2008. May of 2011, they updated them again. And what they did is, each time the operating range gets a little bit bigger. So this kind of faint green region is what it was in 2004. In 2008, they opened it up to the recommended range, and they added in the allowable ranges of A1 and A2. And then in 2011, they said, it's really okay to run things for some hours of the year in A3 and A4, depending on if the equipment manufacturer says it's okay. So you heard Dean talking about, they've worked with their equipment manufacturers. They're going to only buy gear that can run in this larger area. And you saw the impact that Wayne showed. When you superimpose weather data on this, you get more hours. The bigger that you can run that range, you may not run it all the way. When somebody says, I'm going to run my data center up to 85, 35 degrees C. Well, it doesn't mean they're going to run it all the time at 35 degrees C. They mean when it's really hot outside and I can't do anything else except run it at 35 C, I'm not going to shut it down just because of that. I'm going to run it most of the time inside this recommended range. I'm going to run it a few hours way out here in the allowable range, but you know what? I might run it a few hours down here in this allowable range. And it turns out that the way that system reliability goes, that if you run systems hotter than the recommended range, you tend to lose a little bit of reliability, the models that they use for predicting IT reliability, server reliability. But if you run it colder than the recommended range, than the set point where they specify the reliability of the machine, you actually gain hours. So you can run it a little bit above, and you can run a little bit below. You flex around a little bit more. Your systems, you have a little bit more control problems, but your IT equipment's reliability should not be affected by temperature if you do these things. There is. ASHRAE's, when they published the widened specifications, one of the biggest parts of this paper was a commentary about the reliability, and they do calculations that are sanctioned by the IT equipment vendors that say these are the ranges that you can expect if you increase or decrease the temperature, the operating temperature. And they show for a number of cities, when you use 100% free cooling, you'll spend some time above and some time below, and the net effect will be in like 11 of the 15 cities that they profile in the paper, most of the major sites that Jeff's talking about, the impact is either none or you actually get an improvement in the reliability. I also wrote a paper that looks into that a little bit more. It spends a little bit more time. This chart is actually from the Integrated Design Group paper that was published on this, on the impact of ASHRAE on reliability. Because that's one of the biggest reasons that we condition the space at all. is reliability of the IT equipment. And I could go into any IT guy and argue, if you run it hotter, yes, you'll get a few hours. I can almost guarantee you won't be able to see it in your measurements. And if you run it a little bit cooler, you'll get more reliable. And I can almost guarantee you won't be able to see that either. So the net effect is it should be nothing. The changes that you'll see is in the number of hours of potential cooling. So this is the chart that I showed you just a minute ago. These were calculated based on the ASHRAE recommended range in 2011. If you say you're willing to run in those allowable ranges for a few hours a year, this is what happens to them. They turn 100% virtually anywhere in North America and Europe. You could run on outside air 100% of the time. So the chillerless designs that we've been talking about all day long. It's possible. Now you have to have equipment that is Class A3, which not everybody makes, right? This is up to what it runs, I think, is it's a 5 to 40 degrees C for the dry bulb temperature, and 24 degrees C is the cutoff for the dew point. But you can get some equipment like this, and more manufacturers are starting to do this. Dell announced that they have a couple of servers in their line that allow you to do this. You can buy those servers, you can put a data center in Miami or down in Houston and open the windows and let it run all year long. If you listen to guys like Frank Frankowski of Facebook and Dean and other of the big internet providers, they're saying, and the guys from Google, Joe Cava, he says, we're treating our servers way too nicely. We really need to be nastier to them because they can take it. We're just being too friendly to them, so don't coddle your servers. The Green Grid has a tool that you can go and you can calculate the savings that you'll get. You can put in the conditions you want to run at, so you can play around with your inlet temperature. You can play around with your IT load and your location, and it'll tell you how many hours per year we estimate you'll get and what the savings might be on the IT load that you put in there. So it's a kind of a useful tool. It's a public tool that's available on the Green Grid's website. There have been a lot of Economizer success stories. One of the ones that's most significant, I think, is this one about Deutsche Bank. How many of you have heard of Deutsche Bank's data center in Manhattan that's running without 100% free cooling? So I think what Andrew Stokes did here, there are three unique things that I think about this data center that are significant. Number one, it's a mission critical data center. Number two, it's using 100% free cooling in Manhattan or in Jersey City, it's across the river. And number three, it's in a financial institution. So this is not an internet superstar. This is not somebody that is risk accepting, right? Andrew talked his bank into letting him run free cooling because of the significant economic benefit that he would get by doing it. And he's able to show them that I don't need the mechanical chilling. Now turns out he built a DX plant as well in case of a mission critical time, a hurricane's blown over and he has to close the doors for 3 days while the hurricane blows over. But he plans to not use this zone 5 on his chart is where he's using mechanical cooling, and he plans on an annual basis to never use his chillers, never use his DX system. And that's significant. The Green Grid is starting to write a case study about this, so you'll be able to learn more, like the case study that we wrote with Dean and eBay. The Green Grid did publish a study on economizers. We surveyed a little bit over 100 people and asked them, and we were kind of surprised to find already that economizer use is about 50-50. So we found of the folks that we interviewed, about half of them said, yes, we use economizers, airside economizers, waterside economizers, and our average savings is about 20% off of the energy use that we expected without economizers. So that was good. So economizers, that's something you can do. Free cooling is something you could do that eBay and Google and Microsoft are doing a lot of, and that's one. So modular is the second thing. We've talked a lot about modular. There's plenty of examples that we've seen all the way during today. And again, I'm just going to repeat a couple of these things. I call it engineered in efficiency, right? Engineered efficiency, if you have the same solution, like a product, you're going to spend more engineering time on that product. You're going to build it the same way, so you're going to have higher efficiency, better reliability. It's going to be more, this is why Henry Ford invented the assembly line, because he could get more reliability, more production, cheaper than you could by hand building things. And so this is data from a Lawrence Berkeley study where they looked at 7 different container solutions and measured the PUEs that were coming out of those things. And you can see there's one down here that uses outside air as its primary cooling, and these are the kind of numbers that you were seeing with Dean. So Lawrence Berkeley is also getting 1.02, 1.03 for a partial PUE. Now remember, you may have a chilled water plant behind this and things like that, so you can't take that as the only PUE, but these are very low PUE numbers that are because they've engineered in the efficiency into these, into the containers or the modular systems. And people have talked plenty about, the economics of modular, saving time, saving money. I view it as a smaller increment of capacity that is a vice president level decision versus a board of directors level decision. In a company that's going to build a data center, they're going to add a whole bunch of capacity all at once. It's going to take them 18 months or 2 years or 3 years before they bring that online, and then they're going to have 6 megawatts of capacity come online, 10 megawatts of capacity come online all at once. If the green line is your load, your anticipated load, you have to kind of keep that orange line below it all the time. So you're going to make big chunks of capacity if you're buying data centers. If you're going modular, you can make smaller chunks. And down even at the container level, these are a couple hundreds of thousands of dollars decisions that can go with your capacity. You keep them highly loaded, you implement them in a series, or they're modulars inside of a shell that come in a megawatt at a time, even though you have a 10 or a 20 megawatt planned capacity eventually. The more you can keep your systems loaded close to their intended places, their high efficiency points on their curves, the better off you are. The better off you are spending capital at a timed rate, right? Time value money. You keep your capital longer. You don't have to spend it on the equipment up front. There's a lot of advantages on the economics. Microsoft has said, they call this their Generation 4 data center. It looks like a drive-in theater, essentially, right? They're going to put a power spine down the middle. They're going to use free cooling. They're going to have trucks that have containerized systems come in and plug them in. A container has become the new increment of capacity for Microsoft. We used to buy a box, then people started buying racks of computers at a time. Now Microsoft buys a truckload at a time, and eBay is doing the same thing. There's examples that you've seen in different places. A lot of universities. This one is one of the original sons at Stanford Linear Accelerator. This one was at a site in Boulder, Colorado. This one is that's Dean's roof at Phoenix. You can see the Dell and the HP containers there. This one I think is at University of Illinois, up near the Supercomputing Center. This one I thought is interesting. This is close to where I live in Colorado. This is Microsoft's Bing image processing site. So Dean was talking about 50 petabytes of data that he put in. These guys put in 55 petabytes of information of disk in these 2 Dell containers, okay? And they expect to run out of capacity in about a year, and they're going to put in another 55 petabytes of information of capacity in that. These are the guys that, all the maps that you look at and the aerial flies and their free products and their commercial products all go into these sites to be processed and stitched together and light-filled. And it's interesting, you can't find this data center on Bing, and you can't find Google's data centers on Google Maps, but you can find this one on Google, and you can find Google's data centers on Bing. So it's this is literally built in a cornfield in Longmont, Colorado. It took them 3 months. There's a time-lapse video that shows them clearing the site, installing the first couple of containers. There's 5 megawatts of capacity on this site. They expect to utilize it all. This is a cinder block screen wall that's the only construction, and then this is a steel building, a pre-assembled steel building that they put offices in. So very low overhead, very low cost. They're gonna build out 5 acres of this stuff, 5 megawatts, and they're living the dream, right? Free cooling 100% of the time. They don't have chilled water anywhere in there. They just run these things like crazy. It's great. Facebook has done an interesting thing with their technology. They've decided to open source their data center design. How many of you have heard of the Open Compute Project, right? It'll be interesting to see how they're successful they are. They've shared system designs, rack designs, building designs. They really treated the entire data center as a system. They said power's going to come in, Facebook transactions are going to come out, everything in between works together. So they don't have fans in the servers. They pressurize the cold aisle to blow the air through the racks. The racks are specially designed. They have UPSs in the racks. They have all this stuff. And their tagline is efficiency at scale. So back to the dozen or so providers that we talked about, the internet superstars, these are the guys that they want to pal around with. They want to talk to Google and Microsoft and have them buy their servers, and Rackspace and some of the folks that are in that scale. And again, not every enterprise user or small or medium business can take advantage of this stuff, but maybe there are some things. And I'm working with them as the green grid to try and figure out what it is that we can pull from open compute to get into the mainstream of data center and IT design. So now I'm gonna be blatantly lazy and just steal things. These are slides from a presentation that Chris Malone did at a couple of different, and Joe Cava has given this same presentation. And they talk about efficient data centers at any scale. So I'm just going to show you a few of Chris's slides. Because what Chris says is, really the stuff that we're doing, a lot of it is practical and can be done by anybody. And it's not miracle stuff. And you may not get as good as Google, but you can get benefit out of it that's easy to justify. So what Chris says is, fix your cooling first. Use these measures to fix your cooling. Optimize your power, and then keep on measuring and stuff. And let's just look at a couple of the examples that he gives. So the typical PUE is made up of the one that Dean talks about, the compute load, and then there's power and cooling and distribution, power distribution and backup losses, cooling use, and then the lighting and other stuff at 4% or so. And what Chris says, in a typical Google data center, much more of the power goes to the computers, and the cooling load overhead and the power distribution load overheads are much lower. And so he says we do that by a couple of ways. We look at it a little bit differently. So we focus on our infrastructure, our support infrastructure alone, and we only allow certain amounts in our designs. We plan on having very low overhead for each of those systems. And he says, we looked at some of our typical data centers. In fact, they went out and they looked at a bunch of their networking points, which are put in most cases, into a colo facility. They're not in their big data centers. And they said, these were our requirements. We had 2N UPSs, N+2 for the cooling, a bunch of different gear from Cisco and other network manufacturers. And they were designed for, each of these network POPs were designed for about 250 kilowatts. They measured the PUE and they found, on these 5 sites they looked at, somewhere between 2.2 and 2.4. So these are not in their portfolio that they report every year, every quarter, that are the 1.16. But it just goes to show you, even Google has some of these sites. They said, okay, we're gonna do a couple of things. We're gonna look at things that are the highest payback, the simplest to do, and the quickest to implement. They measured that their load was only 80 kilowatts out of their 250 kilowatt design, so they started doing airflow analysis and shutting down equipment. They were able to increase the relative humidity, which Wayne alluded to was one of the big cost items in our PUE study in terms of that. They did a little bit of separation of hot and cold, and they increased the temperature of the cold aisle from, I think it was about 74 to 81. Okay, so they went up 5 or 6 degrees in their cold aisle. They were able to knock 30%, 50% off of their overhead, and they got their PUEs down to 1.5 to 1.6 with their return on investment for all the stuff that they did was about 9.5 months. And they said we didn't do complete cold aisle containment. We didn't implement free cooling. We didn't put modular stuff in there. We didn't affect the overall room temperature. We raised the room operations. We raised the temperature a little bit, but we didn't affect it. And he said this is what it looked like in the end. They built these sheet metal collectors to extend the crack units up higher so that they would draw in warmer air that was up near the ceiling. They put curtains on the ends of the aisles, but not anywhere else. They filled in all the holes in the floors and put blanking panels in, and they get a payback in less than a year. And I think they spent $20,000 and they were saving $25,000 or $30,000 per year in electrical cost in a small implementation. So it just goes to show you that not everything that Google does, are building things on top of hydroelectric dams that not everyone can do. There's a lot of the simple things that you can do either in existing spaces or in your designs that are like the things that Google does. So pay attention to these things. I think that many of these best practices from the IT guys, the internet superstars, are accessible to us. That we can learn from those cases. A lot of them have short-term payback, and even if you don't move your data center to Washington State or you know, in Nebraska, or no, I can't imagine why they're putting them in North Carolina. Well, because of tax incentives, right? It's total cost of ownership that really matters, is the reason that we're getting those things. So I think if you take those lessons from the internet superstars and look at what you can implement, you'll find that there's quite a bit, and the paybacks will be quite good. So thank you very much for your time and attention. I'm happy to answer any questions for a couple of minutes that anybody might have.